So here's the mission. We're going to trace the life of a single prompt. Let's stick with something classic. Write a poem about a robot.
What?
We're going to trace it from the exact millisecond I hit enter to the moment the text starts streaming onto the screen. We are going to crack the black box.
Welcome to Practical AI Forge. Today, we trace the exact journey a prompt takes inside the black box.
Let's get our hands dirty.
All right, step one, the input. I type ROBT. To me, that means a metal machine, blinking lights. But the computer, it doesn't speak English, right? It speaks binary.
Correct. To the raw model, your letters are just meaningless squiggles. It has no concept of R or O or what a poem is.
So it needs a translator.
It needs a translator. Before the model does any thinking or processing, we have to do something called tokenization.
I've heard this term thrown around. Is this just chopping the sentence into individual words?
That's close, but think of tokenization like a Lego kit.
A Lego kit. Okay, I'm with you.
When you buy a Lego set, you don't get a pre-molded castle wall. You get standard bricks, a 2x4, 1x1, little slant piece. You combine those to build a wall.
Okay.
In the same way, the AI has a set of standard subword bricks.
So it breaks the words down into reusable parts.
Exactly. Take a word like unbelievable. To the model, that isn't one giant piece. It's probably 3 Lego bricks snapped together. Unbelieve and able.
That makes perfect sense, because is a brick you can use for unfair or undo. Able works for capable.
Precisely. This is done by algorithms like byte pair encoding or BPE. They've analyzed basically all human text and found the most efficient set of, say, 50,000 bricks to build almost any word.
So my prompt, write a poem about a robot, just gets shattered into these token IDs.
Yep, a list of numbers.
Yeah. Okay, so now the computer has a list of numbers, token 452, token 99, whatever. But a list of numbers is just a spreadsheet. This is where I get stuck. How does it know what those numbers mean? How does it know robot is closer to machine than it is to banana?
This is the moment we enter the math of math. This is the concept of embeddings.
Okay.
And to understand this, you have to visualize a massive grocery store.
All right, I'm in the grocery store, got my cart.
In this store, every single item, every token, has a very specific GPS coordinate. And the golden rule of this store is distance equals meaning.
Meaning things that are similar are physically next to each other on the shelf.
Exactly. You go to aisle 1, shelf 5, you find apples.
Right
next to it, shelf 6, you find pears. They are geometrically close because they share the concept of fruit.
And motor oil is way on the other side of the store.
All the way over in aisle 50. Because the physical distance represents the semantic distance. You've got it. But here's the kicker.
Uh-oh.
This isn't a normal 3D grocery store with aisles and shelves. In a model like GPT-4, this store has thousands of dimensions.
Thousands. I can barely visualize 3.
Nobody can. Our brains aren't built for it. But mathematically, it just means robot isn't on one shelf. It has a coordinate for machinery, a coordinate for agency, a coordinate for metal, for sci-fi, for danger.
So it's this huge string of number.
A massive string of numbers. A vector that places it in the technology sector of this hyperdimensional space. It's near things like circuit and future, and very, very far from medieval or biology.
And this isn't just a metaphor, right? When researchers talk about vector math, they mean you can literally do math with these ideas.
It is literal arithmetic. I mean, there's a classic example from the original research that just blows people's minds.
Go on.
If you take the coordinate vector for the word king, subtract the vector for man, and then add the vector for woman.
Oh, wait. King minus man plus woman.
If you do that math on the coordinates, you land almost perfectly on the coordinates for queen.
No way! That is wild. So it understands queen not by, like, a dictionary definition.
No.
But by where it sits in space relative to king and woman.
Exactly.
Yeah.
It understands that queen is to woman what king is to man. It's all geometry.
Okay, so we've got our prompt. We've turned write a poem about a robot into Legos. And we've located those bricks on this crazy map. But we still have a problem. A list of coordinates doesn't make a sentence.
Right. A bucket of words isn't a story.
If I say the robot cleaned its chassis, I know "its" refers to the robot. But in the grocery store, "its" is just a pronoun. It's in a totally different aisle. How does the model glue these words together into a coherent thought?
Now we have arrived at the engine that changed everything. The reason we are even having this conversation today, the transformer. And specifically, a mechanism called attention.
Attention. I see this in every paper. Attention is all you need.
That's the famous one. To explain attention, we need to leave the quiet grocery store and go to a loud cocktail party.
Okay, I like parties. I'm there. It's noisy.
It's very noisy. And every word in your prompt is a person at this party, all talking at once. The attention mechanism is what allows the model to focus, to attend to the specific relationships that matter while kind of fading everyone else into the background.
So in my sentence, the robot cleaned its chassis. The word its is trying to figure out who it belongs to.
Exactly. The word its is standing there, scanning the room. It's looking for a noun. Chassis is nearby, cleaned is nearby, but robot is the one shouting the loudest in terms of relevance. So its pays attention to robot.
And this happens for every single word at the same time.
Every word, simultaneously. They're all shaking hands with every other word to figure out their context. And the technical way this works is fascinating. It uses 3 vectors for each token: the query, the key, and the value.
Q, K, and V. I've seen this in diagrams. It always sounded like database jargon to me.
It's a really similar idea. Think of it this way. The query is what the token is looking for. The key is the label other tokens are holding up. And the value is the actual information being transferred.
Okay, can you ground that in the robot example?
Sure. The word its sends out a query that's basically like, I am a possessive pronoun looking for a subject owner.
Right.
And the word robot holds up a key that says, I am a singular noun, and I am the subject of this sentence.
And they match?
The math says click, they match. So robot passes its value, its whole semantic meaning, over to its. Now, the word its isn't just a generic pronoun. It's become the robot's possessive. It has absorbed the context.
That's remarkably clever. It's like it rewrites the meaning of the word based on who it's standing next to at the party.
I remember this is multi-head attention. You hear that term a lot.
Right, multi-head. That just means it does this a bunch of times in parallel.
Yep. Imagine having like 12 different pairs of ears at the party. One head is listening purely for grammar, like we just described. Another head is listening for tone. Is this a sad poem or a happy one? Another might be checking for rhyming schemes.
And they all combine that information.
They all gather that context simultaneously and combine it.
So at this point, the model really understands the prompt. It has the definitions from the map and the context from the party.
It has a rich contextual representation of your request.
Yeah.
But now it runs into a physical limitation. And this is something every single user has experienced.
The memory loss.
The memory loss. You're having a long conversation, you're pasting in code, and suddenly the model forgets what you said 5 minutes ago.
Yes. It's so infuriating. It's like it just gets amnesia.
That is the limit of the context window. And the best way to visualize this is as a workbench.
A workbench. Okay.
Imagine the AI is a genius carpenter, but their workbench is strictly limited. Let's say it's exactly 4 feet wide.
And that's the context window.
That's it. The carpenter can only work on projects that fit on that table. Every time you type a new prompt, you're sliding a new blueprint onto the table, and it takes up space.
So what happens when I add one more sentence?
Well, physics takes over. To make room for the new words, the oldest blueprint on the far side just
slides off the back edge.
Slides off the back edge and vanishes into the mist.
And once it falls off the table,
It is gone. Totally deleted from the calculation. The model doesn't have a hard drive of your conversation. It only knows what is currently on the workbench.
that explains so much. But wait, there's a nuance here that bugs me. If the table's full and I ask a new question, does it have to reread everything on the table to answer me? That seems incredibly inefficient.
You have just hit on the biggest bottleneck in AI speed. It's called quadratic complexity. If it had to reprocess the entire conversation from scratch for every new word it generated, ChatGPT would take hours to reply to hello.
It would be unusable. So how do they fix it? Because it feels instant.
They use a cheat code called the KV cache, the key value cache.
We're back to the keys and values from the cocktail party.
Exactly. Remember those handshakes? The math of how robot connected to it?
Yeah.
Well, the model realizes, hey, the past hasn't changed. Robot is still robot. So instead of recalculating all those social connections every single time, it saves the keys and values in a cache. It leaves the math sitting on the workbench.
So when I type a new word, it only has to do the math for that one new word and check it against the cheat sheet.
Spot on. It changes the workload from quadratic, which gets exponentially harder, to linear. It's like keeping your notes open on the desk instead of rereading the whole textbook every time. That's why the text streams out at typing speed.
Okay, so we've processed the input with Legos, mapped the meaning in the grocery store, established context at the cocktail party, and managed our memory on the workbench. We are finally ready to write.
The output.
How does it actually choose the words? Does it write the whole poem in its head and then just paste it?
No, and this is crucial. Large language models are autoregressive, which is a fancy way of saying they generate one token at a time. Just one. It looks at everything on the workbench and asks, based on all this context, what is the most statistically probable next Lego brick?
So it's literally guessing.
It's predicting probabilities. It looks at its entire dictionary and assigns a percentage chance to every word. If the sentence is, the robot is made of, the word metal might have a 20% chance, steel might be 15%, cheese might be 0.0001%.
Okay, but this is where I get skeptical. If it's just math, if it's just picking the most likely word, wouldn't the output be incredibly boring?
Yes.
I don't want the statistically average poem. I want something creative.
You are absolutely right. If you always picked the number one most likely word, the text would be dry, repetitive, robotic. We call that greedy decoding. To fix this, engineers give you a control dial. We call it temperature.
Ah, the spicy dial.
I've seen this in the API settings.
Think of it exactly like a spicy dial. If the temperature is low, say 0.1, the dial is set to vanilla.
Safe.
Very safe. It'll almost always pick the number 1 or 2 probability. It's precise, factual, but boring.
And if I crank the dial up, if you turn it up to spicy, say 0.8 or 1.0, the model starts taking risks. It might ignore the number one choice and pick the word that was ranked 5th or 10th. It essentially throws a dart at the menu.
And that randomness is the creativity?
That's all creativity is in this context. It's controlled randomness. It's the model saying, instead of the robot is strong, I'm going to say the robot is unyielding. It's a lower probability word, but it adds flavor.
But if you go too high, if I just max it out...
Then you've overdosed on spice.
Yeah.
It starts picking words that had a 0.001% chance. It starts speaking gibberish.
So there's a sweet spot.
Exactly. And engineers use filters like top out to basically cut off the bottom of the list. They say be spicy, but don't pick anything from the bottom 10% of nonsense.
Okay, so that explains how we get words, but I have a safety question. If this model was trained on the entire internet, and let's be honest, the internet's a nasty place, why doesn't my robot poem come out full of slurs? Why is it usually so polite?
That is the wild wolf
The
problem.
wild wolf.
The raw pre-trained model, the thing that just read the internet, is like a wild wolf. It's incredibly smart, but it's feral. If you prompt it with a conspiracy theory, the wild wolf will just complete the pattern and give you more conspiracy theory.
It doesn't care about truth or safety.
It only cares about completing the pattern, so we have to tame it.
So how do we do that?
We send it to obedience school. This is the process known as RLHF reinforcement, learning from human feedback.
Dog training school.
Literally. Companies hire thousands of humans. If the wolf writes a helpful, safe poem, the human gives it a treat, a positive reward. If it writes something toxic, the human says, bad dog, a negative signal.
And over time, the wolf learns to act like a house pet.
It learns to simulate a helpful assistant. We're now moving to a newer, faster version called DPO, Direct Preference Optimization, where we just feed the thumbs up, thumbs down data directly in. But the result is the same. You turn the wild wolf into a helpful Labradoodle.
The Labradoodle of math, I love that.
It's a polite facade over a wild engine.
Okay, so we've successfully written our poem. The robot with a heart of steel, in circuits vast, it learns to feel. It's polite, it's creative, it followed instructions.
Success.
But let's throw a curveball. I'm not satisfied with text. I want a picture. I type, generate an image of a sad robot. Does the transformer do that too?
No. And this is a super common misconception. If you are generating images, you are switching to a completely different engine.
Yeah.
You are leaving the land of transformers and entering the land of diffusion.
Okay, quickly, how does diffusion work? Is it predicting the next pixel like the other one predicts the next word?
No. Prediction is for text. For images, the metaphor isn't a writer, it's a marble sculptor.
A sculptor.
Imagine a solid block of gray stone.
Right.
But in the digital world, this isn't stone, it's noise. Just pure static, like an old TV tuned to a dead station.
Right, pure chaos.
The diffusion model has been trained to look at that static and denoise it. It acts like a sculptor chipping away the stone to reveal the statue hidden inside.
So it starts with chaos and carves out order from it.
Yes. It looks at the static and says, based on the prompt sad robot, I think this patch of static looks a little like a metal shoulder, so it clarifies those pixels. Then it says, this looks like a glowing eye, and clarifies that. It runs a reverse process.
Reverse.
Well, the training involved taking a clear picture of a robot and slowly adding noise until it was totally ruined. That's the forward process. The AI just learned to reverse that, to subtract the noise step by step and recover the image.
So when I see that loading bar on an image generator and the picture gets clearer and clearer,
You are watching the sculptor chipping away the noise, revealing the image that matches your prompt's coordinates in the grocery store.
wow. Okay, we have covered a massive amount of ground, from Legos to sculptors.
It's a lot to take in.
Let's just recap this journey, just to lock it in for everyone listening.
Let's do it.
I hit enter. The model smashed my prompt into Lego bricks.
The tokens. Check. It found the meaning of those bricks by looking up their coordinates on that massive, multi-dimensional grocery store map.
The embeddings. Check. It figured out the context by sending the words to a cocktail party, where they listened to each other to find out who was relevant.
That's attention. Check.
It managed the flow of conversation on a tiny workbench using a cheat sheet.
The context window and KV cache.
Yeah.
Very efficient.
It then used the spicy dial, the temperature, to creatively predict the next word.
All while behaving like a trained Labradoodle because of RLHF.
That is actually a really coherent system when you break it down like that. It makes the magic feel manageable. It's just mechanics.
It does. It's a marvel of engineering.
Yeah. Well, I have to say, the magic is gone for me now, but it's been replaced by a huge amount of respect for the engineering. The math is actually cooler than the magic.
I agree.
I love that. So the next time you see that cursor blinking, waiting for a poem about a robot, just remember, you're not talking to a brain. You're exploring a map.
Thanks for watching. If Gen AI feels a little less like magic now, that was the goal. Consider subscribing for more practical, grounded AI explanations. See you in the next video.